I have 20 nice low-profile mechanical switches for my homebrew calculator, but only 7 GPIO pins on an Adafruit Feather. I gotta figure out what to do about this. The first step is to quickly eliminate a bunch of pins by connecting the keys in a 4x5 grid so I can test each column at a time and check to see what the rows output. If any of the keys are down in that column, then they will output the same voltage on the output of the rows. And voila, you have a keypad input. But 9 GPIOs is still too many. I only have 7, and I'd really like to use a fair number of those 7 for other things if possible. The first option, of course, is let's just use our analog pins as GPIO. I really don't want to do that because it might make the calculator incompatible with other feathers or wings, and I would be limited by what I could plug into it. The feather spec doesn't specifically say you can't, but they ask really nicely that you don't. Oh, here's an idea. I could use some of the GPIO pins to connect a shift register to the keys and shift that out as serial data into the processor. I would need 1 pin to activate the parallel load, 1 pin for the serial clock, and 1 pin for the serial data. I would also need 4 pins for the columns to activate each column and so I could read the output on the rows. That's 7 pins total, which yay, it's down to our 7 max, but still doesn't leave us enough pins to do anything else with the GPIO. Oh, but you know what? Better yet, I could use 16-bit registers. I would only need 2 of those to cover the entire 20-key keypad. That's a lot better. I'm down to 5 pins now. Got 2 GPIOs back. Feathers have dedicated I2C pins though. I wonder if there's a shift register out there that could actually speak I2C protocol and I could just connect it up to those pins instead. Wow, yeah, there it is. That took a little searching, but apparently they are called I/O expanders. They allow you to send I2C commands to the chip and then it manages the capture of the inputs. This is exactly what I need. I can use 2 of these to control the state of the rows and the columns on the keyboard. I could probably just use 2 shift registers and I would allow me to scan the keypad using I2C. That requires 0 GPIO from the Feather. I get all 7 pins back. That's incredible. I have achieved ultimate success with my pinout. There's still some complexity here. I need to send roughly 9 commands in order to read the full state of the keypad at any given time. Those 9 commands adds up over time. In order to accurately read the keypad, I have to scan the keypad hundreds of times per second, probably several hundred, and write some code to actually do key debouncing. I can do that, but I wonder if I could eliminate some of those by just having a larger I/O expander. If I had at least 20 pins on my I/O expander, future me here, the eagle-eyed among you may note that the C110, the Commodore calculator that inspired this project, has only 18 keys plus a constant switch. I decided that I would use a key instead of a switch for the constant function, and then use 3 standard size keys at the bottom rather than the 2 larger ones on the C110. Thus, my calculator, the GK110, will actually have 20 keys. Then I could just read the entire keyboard in one I2C cycle. If I run the math out correctly, it would save me 67% of the time to scan the keyboard, which is quite a bit of processor savings. Not a big deal for a calculator, but worth trying to minimize. I think I'm getting closer and closer to a great solution here. The largest in-stock I/O expander that I can find on Mouser is 16 bits, so I would actually need 2 of them. So I'm reading in 2 cycles. That's much better. I noticed that there's several of these that have an interrupt pin on them, so they can detect if any of the I/O changes and then send an interrupt to the processor. I only have to pull the keyboard details when one of the interrupts is high or low, depending on if it's active high or active low. That's gonna be a really big efficiency saving. All right, so far, the best solution has 0 GPIO needed, but I can use 1 for the interrupt to save some processing time. I will admit, I was gonna stop there, but during my research on these 16-bit I/O expanders, I ran across something really cool. I give you the keypad decoder. What? This is exactly the same like I was doing with the 9-command version, but instead of the processor having to actually pull all of the rows and columns, this chip has logic on it to do it itself. It then stores those events in a set of internal registers, which then I can read over I²C. It also has an interrupt pin. I don't have to do any polling. It has debouncing logic, so I don't have to write that myself. As a bonus, unused pins can also be used as other GPIO. This is definitely the choice I'm going with. All of the communication happens over I²C except the interrupt. Now I just need to work up a schematic and PCB in KiCad. After creating the symbols and PCB footprints, I plop all those onto a KiCad schematic. I put the keypad controller there, connect it up to the keys in the 5x4 grid, connect the I²C lines to the dedicated I²C pins on the feather. The first version will just be a development prototype board, and I will plug that board into a breadboard instead of kind of designing the full calculator. That'll let me iterate quickly, test everything out, make sure that it all works before I try to go straight to a final PCB design for the calculator. Initially, I was just planning on having a single feather socket that I could plug a feather into, but I realized this PCB with the dimensions I'm using actually has a perfect amount of room for 2 of them, so I'm going to get 2 instead. As you can see here, I'm laying out the keyboard. This gets a little tricky, not for space reasons, but because all of the wires need to cross each other. I also have all of these connections that need to be made between these adjacent feather sockets, and getting those in all the right places through this pretty tight space was actually rather difficult at the time. But in the end, I worked it out. That is a really small integrated circuit in the middle of that board there. So after I get everything initially laid out, I always have to go back and clean up all of the traces and make sure that they're laid out nicely, usually space them out a little bit more even than the first time. I also want to make sure the silk screen has all the letters and numbers of the keyboard on it, and so that's what I'm doing here. And I am just about done with this PCB. Yes, I'm gonna make that last key pi. That's what the extra key is gonna be. Sweet. I always like looking at the 3D render of the board, making sure I've got all the labels and the silk screen properly worked out. Yeah, this looks nice to me. Someday I'm gonna work up a Grok This logo I can put on a silk screen. I'm gonna double check everything off camera so that you don't have to watch me meticulously go through it. Well, it looks like we solved our mechanical keyboard problem. If you wanna know more about why I'm building a calculator with mechanical keys, you can check that video out where I revive my homebrew project. Of course, the next problem that I have is I don't actually know how the I²C protocol works. I have to learn how it works and teach my processor to speak I²C. If you want to see that, you can check out this video as soon as it's out. All right, in the meantime, I'm gonna go quadruple check my schematic and PCB layout, make sure I got all the voltages and everything right, and order this PCB. See you next time.